Actually, there are mainly two applications based on our practical examples. So these applications actually we'll be doing in our laboratory mostly. But nowadays, because of this corona lockdown and all, people are not able to do hands-on experiment. But still, I think your uh, respective schools will do some virtual experiments in lab. From there, excuse me. So from there also you'll be able to have some flavor of doing some experiments in the laboratory. So basically, we'll be learning today Wheatstone bridge and its application as meter bridge and potentiometer. So in these two instruments, we'll be applying the Kirchhoff's KVL, KCL, etc. To find out, see, meter bridge or Wheatstone bridge we use to find out unknown resistance. And in many electrical or electronic circuits, this Wheatstone bridge is being used. And potentiometer, as you can understand, potential or potentiometer, it is coming from potential. So if you have unknown cell, electric cell, what is the EMF of the cell, you can determine from the potentiometer doing some simple experiments. And also internal resistance, you will be able to find out for a respective cell. If you know the internal resistance for a standard cell, you can just compare with that, and then you can find out the unknown resistance for another cell. So we'll first see the Wheatstone bridge. So so this is actually it looks like a complicated circuit, but once I explain, you'll see this is very simple circuit. And this circuit has 4 arms. Okay, so how many arms? You can see this circuit has 4 arms. So this is one arm. This is, suppose this is first arm. This is second. This is third arm. This is fourth arm. So you can see this is a kind of a square. Okay, kind of a square made of 4 different resistance. Okay, 4 different resistances, and you can see this. Remembering the circuit is very important in our application purpose or in our practical purpose. When you go for laboratory exam, this circuit diagram will not be given to you. You have to remember the circuit diagram, and then you have to make a proper circuit with wires and cells, resistors, and many other electrical components, and you have to perform the experiment. So it is very good to remember the circuits itself. So how do I remember this circuit? Suppose I have 4 resistances, but we need to know between which points R1, R2, R3, and R4. So if you cannot see, I'll just write this is R3, this is R4, this is R2 resistance, this is R1 resistance. Okay, so you have to rigorously remember between which 2 points. See, this is A and D. Between A and D, this resistance R1 is connected. Then you should be remembering that between A and B, R2 is connected. So R1 is called arm, first arm, first arm. Similarly, so R2 is known as second arm. Okay, then R3, this is known as third arm, and R4, resistance R4 is known as fourth arm. Okay, so this is how you can remember like between which two points, which arm is there or which resistance is connected. Okay, now say to do any experiment with electricity or electric current, you need a source which can give you current. So look here, the cell having EMF E is connected, see, between two diagonally opposite points, that is A and C. So between A and C or across A and C, you have to say across A and C, the cell of EMF E is connected. Okay. Now we have B and D. Between B and D, there is a device called galvanometer. What is that called? This we will learn again in our fourth chapter, construction of galvanometer. Galvanometer. What is the use of galvanometer? It can detect.
Sir, it can detect the current.
It can detect
Current.
exactly. It can detect the current in the circuit. Okay. So you'll see in practically what will happen. So there will be see kind of a device. So there will be two knobs, so through which you can connect the wire to circuit. Okay, and see there will be here a needle. Okay, this will be like in a case, plastic case. Inside a plastic case there will be a scale like this. So here, suppose this is a 0 point or 0 scale, like in thermometer and all. See, you see there will be graduation, right? So that you can understand how much. So here you look, this 1, 2, 3, 4 like that. There will be graduations, okay? And this side also 1, 2, 3, 4 like that. There will be graduations, and there will be a needle, okay? Needle like this. There will be a needle. So when there is a current, there is no current, then the needle will be exactly pointed to the zero line, okay? The zero line. But whenever there is a current flowing through this, there will be deflection. So suppose, see, some, if this is a milli ammeter, okay, so like it has a range of ampere, okay, kind of milliammeter. So there is another device called milliammeter or ammeter that also give you, actually this can detect the current whether there is a presence of current or not. But ammeter can directly give you how much current is there in the circuit. That is called ammeter. So galvanometer can detect the presence of current, and ammeter can give you the value of the current, value of current. Okay. All right. So what it shows, actually, it will just, so if some positive current is entering into the galvanometer, it will just immediately show a deflection. It will come here, somewhere here, okay, somewhere here. The needle will come, and immediately it will go back to zero, like that. Okay. And similarly, if your negative current is there, so from zero to the negative side, it will just deflect towards negative side. Okay, deflect towards negative side, like left of zero, that is negative, I am saying. Okay, otherwise if there is no current, then the needle will be at the center. Okay, so if you look some demonstrations in the YouTube videos, maybe you will be able to understand better what is the use or what is a galvanometer, ammeter, etc. Okay, or maybe when you go through some virtual experiments from your school laboratory, you will be able to understand better the options of like uses of this galvanometer and all. All right, so now look, so this is a brief, so I could understand the circuit diagram now completely. So I hope so you have understood. This is first arm, this is second arm, this is third arm, this is fourth arm. I'll tell you why this is called unknown and this is standard. We'll tell you later. And see, between A and C, diagonally opposite terminals or points or vertices, we have connected a battery, okay, having EMF E, and between B and D you have connected galvanometer. So this galvanometer can detect the presence of current. If there is current passing through this, okay, some current Ig suppose, then it will show a deflection in the needle. If there is no current, there will be no deflection. So in our practical purpose, like we will actually work with this bridge at null condition. What is that? Null condition, or it is called balanced condition. Balanced condition of the bridge. Balanced condition of the bridge. So what is this balanced condition of the bridge? That is actually special cases. I'll tell you. See, the current is actually, see, from the battery. The current, suppose some current I is flowing from this battery to, see, it goes up to A point, right? Now see, I know KCL. So if I apply KCL over here at A, so this current, total current will be getting divided into two. So suppose this is through the through the second arm is R2, and through the first arm it is I1. So it gets divided into two parts. Okay, so I2 goes up to B point. Then look, there are two paths. One through the galvanometer and another path is through the unknown resistor or the resistor 4. Okay, resistor 4. So suppose the current Ig is flowing through this, then this current will be, see, this current I4 actually will be, see, this is I4. If this is I4, so actually the current will be, I4 is I2 minus Ig. Then it will be I2 minus Ig. I hope you agree with me from the KCL I am writing. Okay, so here, then how much current comes here? I4 means I2 minus Ig comes up to C point. Okay, now look here at this point. At this point, see, this is I1 coming up to here, and say another current Ig is coming up to here. Ig is coming up to D point. So these two guys will add up over here. So this will constitute current I3, which I can write I1 plus Ig, right, from KCL at point D. Now this current will go, I3 will go up to C and meet with another current which is coming from B. So look, this current is I2 minus Ig, and another current is this one. So this is, suppose, yeah, this is I1 plus Ig. If you just add them up, then you get the total current I. So now it will come as I over here. Okay, so see, I1 plus I2 is I, right? This is how we are applying KCL over here. Okay, now look, we, as I said, will be talking about null condition over here. What is the null condition? Null condition or balanced condition of the Wheatstone bridge is a condition when there is no current flowing through Ig. That means what? That means Ig is equal to 0. No current is flowing through the galvanometer. That means when you cannot see any deflection in the galvanometer needle. So Ig is 0. So if Ig is 0, look from here. If Ig is 0, then what are the values of this current? See, if Ig is 0, I4 is nothing but I2 because it is not getting divided into Ig and I4, etc. So I4 is equal to I3, sorry, I2, and I3 obviously will be equal to I1. Okay, that means I can say that through, like, A to B, A to B, and B to C, only one current is going, same current is going, that is I2. Okay, this is I2. Similarly, through this path A to D and then D to C, the same current is going. What is that? I1. Okay, I1. That means I3 is equal to I1 and I4 is equal to I2. Okay, so with this, let us see when there is a like there is a balanced condition, what are the ratio of this first term, second term, third and fourth term, like that. Okay, what is the ratio of this resistors? Actually, that is the main aim for this bridge. So this R4 is sometimes known as unknown resistance. Okay, that means if you have the first term some fixed resistance, second term some fixed resistance, suppose this can be like different value, having different value R1 and R2, different values, but fixed resistance, they don't change. But this standard resistance, sometimes it is written as S also, sometimes it is written as S also. So this R3 is written as S, that means standard resistance. So this standard resistance, okay, this standard resistance can be varied. Okay, you can know, suppose you are adding see R4 is also a fixed resistance, but that is unknown resistance, we don't know what is the value. So I have to find out the value of R4 with the help of this bridge. So my R1 and R2, okay, R1 and R2 and R3, so R1 and R2, they will be fixed value, having fixed value, and R3 is a standard resistor. You have some resistance box, suppose, okay, from where you can connect some resistance to the circuit. So you will be able to understand. You have suppose added some 10 ohm fast, then 100 ohm fast, then like that you can vary. So you can vary until you see the null deflection. That means there is no deflection in the galvanometer. So you will be varying the resistance in this standard arm until you see a null deflection. That means there is no deflection, or in other words, there is no current through the galvanometer. Okay, so till that condition you will be varying the standard resistance. Look, we'll see how we can use that condition, balanced condition, to find out the unknown resistance. In fact, I'll tell you the result first. What we'll get? We'll see. We'll get like this: R1 by R2, and at the balanced condition, we'll get this equation: R1 by R2 is equal to R3 by R4. So from here, you can directly get R4 is equal to R3. Uh, yes, R3 by R1 into R2, or I'll write in another way. So R2 by R1, okay, R2 by R1 into R3. So this R3 is the standard resistance. You can vary this, okay. Then this is your known value, and these are having fixed value. So you know the ratio of these two, and you know how much resistance you have connected to the circuit to get a null condition, okay. So using this ratio, then this is actually the condition, balanced condition. This is the condition for null deflection. This is the condition for null deflection, or null deflection, or zero deflection of the galvanometer needle. Okay, so we'll derive this equation. Let us see how we can derive. So as I told this, we'll be using the Kirchhoff's law. Look how we can write the Kirchhoff's law. So first I'll take this loop, okay, this loop. So I'm going through A to B. So this is suppose loop 1. A to B to galvanometer, then to D, and D to A. This is loop 1. So if you can volunteer, you can tell me what I'm writing the KVL, okay? KVL in this loop, or loop rule, is of loop rule. So what I can write is, see that voltage drop across across the resistors, okay, and we have to see whether there is a battery or cell. We can write in the, see, actually I have told you, so this will be IR, summation over IR is equal to summation over the battery EMF. This is KVL. They have to be equal, or or else you can write as this, is equal to 0. So whatever convenient for you. So I generally prefer to write like this: summation over IR is equal to summation over the EMF of the battery involved in the loop. So we have actually learned this thing with two, three applications in the last class. So you can refer the last class. If you don't understand, you can ask me again. So look here, what I can write is in the loop 1, this is L1. So I'm going from A to B, B to G, G to D, D to A. So what is the drop across R2? I2 into R2. So what is the drop across this BD? There is no current through galvanometer. So there will be no drop at all. Okay, this will act as a simple conducting wire. There is no drop at all. So now I'll go to D to A. What is the drop across this R1? And we have to see, I have told you that while taking IR, this drop, you need to see what is the direction of the current and which direction you are going through the loop. Okay, going through the loop. So in this case, you look, I'm going to D to A, but current is flowing from A to D. So here, obviously, you have to take minus I1 R1. Okay, and what is the cell EMF? Is there any cell involved in this? No. So it is 0 right hand side. So what I get is actually I1 R1 is equal to I2 R2. Okay. Similarly, look, if I consider another loop, this one, okay, so it is loop 2, suppose this is L2. I am going from B to C, C to D, D to G, and coming back to B. So in this loop, so see in the first we have got from the first loop, this is equation number 1, suppose. So the B to C, C to D, D to G, and B, like that I have a loop now. So I'll write, see, I4 into R4, then C to D. See, the current direction is opposite. I'll write I3 into R3. Okay. And look this, I'm going from D to G. There is no current over here. So this potential drop is 0. And there is no cell involved here. So right hand side is also 0 here. Okay. Look, if I simplify a little bit, so what I'll get this as uh, I3 R3 is equal to I4 R4. This is what I'll get. Now look at the balance condition what I had taken, that Ig is 0. So if this Ig is 0, that there is no current to the galvanometer, then I4 is equal to I2. I4 is equal to I2 and I3 is equal to I1. So if I just substitute them, then see I3 is equal to I1, so I1 R3, and this is I2 R4. I can write like this. Okay. Now look, if I take the ratio I1 by I2, what I get from here, I1 by I2, I'll get R4 by R3. Okay. So yeah, this is what I will get. And now look, from equation 1 also, if I take the ratio I1 by I2, what we get? So we'll get I1 by I2, you will get R2 by R3. Okay. So these are the ratio of same quantities. So I can equate them up. So I can just equate them. So if I equate them, look what we'll get. We'll get R2 by R3. Oh, I'm sorry. Here it will be R1. R2 by R1. So R2 by R1 is equal to R4 by R3, like this. So from here, you look, R4 is equal to R4 is, so R2 by R1 or R1 by R2 you can write, and then it will be R3 by R4. So this is the balance condition which we require, okay, for a bridge, okay, Houston bridge. If there is a Houston bridge given and all the resistances are given, they will be asking you to find out whether this is at a balanced condition, or some question will be given and you have to find out whether there is this bridge is at balanced condition or not. What you have to do, you have to take this ratio of the resistance, okay, and then see, like resistance in the second arm by first arm is equal to resistance in the fourth arm divided by, so this ratio, if this ratio, actually if this is satisfied, then the bridge is at balanced condition. So at balanced condition, I can use the bridge and I can find out the unknown resistance. R4 is equal to, I can write R2 by R1 into R3. Okay, so I can see, I know the ratio of this because there's a fixed ratio, fixed resistance, and I can vary the R3 value of the R3, okay, until you get the null condition, and then using this we can find out the unknown resistance. That is why R4 or the fourth term is written as unknown resistance, and this R3 is written as standard resistance. I hope you people have understood this. So see, this is Houston bridge. An application of the Houston bridge with the, actually in the laboratory we have model an experiment with the concept of this balanced Houston bridge. So that is called meter bridge. You can see I have kept this meter. This is a meter bridge actually, and meter bridge, and this is Houston bridge, which we have already learned here. Look, actually this meter bridge is equivalent to Houston bridge. How we'll understand that? And with the help of this meter bridge, in our laboratory, we can find out unknown resistance. Suppose this is unknown resistance R. This is standard resistance as you have learned. This is two arm, you can easily see. Another two arm we have to find out from here. Okay. So, and then with the help of this condition, R1 by R2 is equal to R3 by R4, this balance condition, we can find out unknown resistance. This is the practical application of this Houston bridge concept. Okay, this is meter bridge. Okay, let us look. We have to compare, as I told you, that you have to compare, you have to actually thoroughly remember the arms, different arms, like which arms, where which arms are connected. So if you remember that, with the help of that, you can actually solve the problem for meter bridge because they are equivalent circuit. Okay, they have equivalent circuit. Okay, look how. See, let me tell you first the constructions of this meter bridge. Actually, this whole thing will be on a wooden plank. Okay, wooden plank or wooden board. This experiment. So what are there in this meter bridge? See, there are actually two L-shaped or rectangular. Sorry, uh, like two. See, these are actually metal strips. These are L-shaped. They are a right angle. See, they have right angle here or right angle metal strip. Okay, which are actually uh, stick on the wooden board. Okay, and another metallic strip. This is same material, actually having same material. All the metal strip. These are metal strip. Okay, thin but wider metal strip. These are L shape, and this is a straight metal strip. And look, what is the use of this strip to this metal strip to keep like that, to make the gap. So this is gap 1, this is gap 2. So there will be two gaps formed between this L shape and this straight metal strip. Okay. Okay. So and this, in this gap, so between these two gaps, one gap, in one gap unknown, an unknown resistance has to be connected, and the other gap a standard resistance has to be connected. Okay, so two arms I have got. What are this? The unknown arm and standard arm I have got for this meter bridge. Okay, now another thing, one, look here, the name itself is saying as meter bridge. So there is a meter scale over here. You look here and look this. So in between this A and C, that means these two L-shaped metal strip, just below them, okay, there is a 100 centimeter or 1 meter length wire. Okay, it's a wire having 1 meter length is connected just at the end of this L shape. See here below, here to here, you can see this. So this is a 1 meter wire or 100 centimeter wire. Okay, and this has uniform cross section. That means it is uniformly. It has a fixed radius. Okay, uniform cross section. Uniform cross section. Okay, and obviously this wire is a conducting wire, and every conducting wire will be having certain resistance. Okay, and as you know, if you increase the length of the wire, resistance increases. Okay, so if I connect this wire different length of the length to the circuit, so different amount of resistance will be connected to the circuit. Look again, see at the end of the A and C, across A and C there is a battery, or you can think that the wire itself is connected. One end, that is at C, one end of the wire is connected. In fact, both the ends of the wire is connected to a battery or a cell through a key. Through a key. Okay, through a key. And you can see there is a meter scale. Meter scale, there is a purpose to measure the length of the wire, how much we have added to the circuit, how much of the length of this wire has been added to the circuit or connected to the circuit. So to know that, this meter scale is needed. So suppose from here it is 0, then maybe some 30 centimeter, then it is maybe some 60, 70, 80. Okay, maybe this is 70 centimeter, this is 80, 90 and 100, like that. Okay, so this is a meter scale. So maybe starting from 0 from here. Now look, so between C, if you just compare the circuit, look, see across A and C there was battery or cell in this Western bridge. Here also it is there. And between B and D there is a galvanometer. So where is B over here? See on the straight metal strip there is a point B here, and that means there is a connection. Okay, through the wire to the galvanometer. Okay, so this is BD, sorry, B and G, this is galvanometer, and other end of the galvanometer is connected to a jockey. Jockey are actually shaped as triangular like that, and at this place there will be a sharp knife edge. Once you go to the laboratory and do the experiment, you will understand what it is. So it can see, it can actually slide over, slide, and then see, I'll just draw separately again. Okay, so suppose this is a jockey, what it can do actually, a jockey can do, so it can slide over the wire. Okay, and see there is a knife edge. As soon as we tap the knife edge this at this wire, so this much of the length will be connected to the circuit. Okay, suppose this is L1 and this is the rest of the length. Okay, rest of the length, this will be connected to some other end already. Okay, so this is the purpose of a jockey, it can slide over. If you are not getting the null condition of the galvanometer, you can slide up to here and get the null condition, and this length will be one arm of the Houston bridge, and the rest of the end will be another end, another arm of the Houston bridge. In this case, look what I'll show you here. See, the D point is actually with the jockey, and that can be varied. So D can be here somewhere, D can be here, as the jockey can slide over. Okay, D can be here. So how to determine the position of the D? Just by seeing the reflection of the galvanometer. As I said in the beginning, that we will be using the balance condition of the Houston bridge or null condition of the Houston bridge in this meter bridge, okay, and we'll be finding out the unknown resistance. So now we can see if the jockey is tapped over here at D. So AD, this certain length, suppose this is L1 length. So this L1 will act as one of the arms. Look, what is that? A between A and D. This is R1. Okay, right? So see AD here, the length actually L1. This will be equivalent to your R1 arm or first arm. Okay. Then look AB, between A, B, C, this R is given, unknown resistance. This is equivalent to your AB means R2. Okay, this is equivalent. This is a very simple way to remember. Okay, otherwise arbitrarily you may not be finding out the arms. Okay, we'll just compare between this Wheatstone bridge and meter bridge, and we'll compare the resistance of which one is which arm, like which one is equivalent to which arm. So between B and C, look, B and C, this is R4. So between B and C, see here it is given S, which is equivalent to your R4. Okay. Now see AD I have got. Then DC. DC is equivalent to your, see, this is uh 100 centimeter minus L1, then remaining length of the wire. Okay. So which is equivalent to your R3. Between D and C, see Wheatstone bridge Rn3. So this is this kind of so this is R3. So in this case, if we apply our balance condition of the Wheatstone bridge, so I hope you people have understood. So how to find out the arms in the meter bridge? Okay, since it is equivalent to Wheatstone bridge circuit. Okay, we'll compare between B and D. There is a galvanometer. Between across A and C, there is a cell. Here, look, across A and C. So between A and D, we have taken first term. So B and D, sorry, A and D. This is your first term, which is actually equivalent to your L length. Now look, what I'll do. Suppose since this wire is uniform, that means what? It has resistance uniformly, like uniform resistance. Okay, uniform resistance. So I can just take a constant for that. See, if I suppose that RCM is the resistance per unit length of the wire, that means R by, this is actually yeah, R by L. If this is the case, L is the total length. Okay, this is, or I can write even 100, R by 100. That means each centimeter it has this much. So if I know that your AD arm is at 50 centimeter, what will be the resistance? So your resistance will be, so RCM into 50. Okay, that means your resistance will be R by 2. If you know the total resistance of the wire, then you can find out the resistance for each and every length of the wire. Okay, so suppose this is a resistance per unit length, RCM, resistance per unit length. So this constant will be given in the laboratory. Okay, or total resistance of the wire will be given. You have to divide total resistance by 100 to get RCM. Okay, so if I know that, see, now I have already compared. AD is corresponding to your L1. So L1 means how much resistance? L1 means RCM into L1 resistance. So this much resistance is equivalent to your R1. So I'll be using the ratio. So yeah, I think I'll clean this portion. I'll write it here. So we have learned DC. DC actually it is 100 minus L1. Okay, into RCM. This much is the resistance, which is again equivalent to your R3. Okay, and this R1 is equivalent to how much resistance? Or L1 into, so it is A into AD. This much length of the wire is actually equivalent to your first arm. So this much is the resistance, L1 into RCM. Okay, now I'll write the ratio. Look, say R1 by R2 and the balance condition of the bridge R3 by R4. Okay, all right. Or I can write. Okay, let me just write this. Let us put the value of this R1, R2, and R3, all those things. So here, this gives us R1 is actually L1 into CM, RCM. Okay, what is your R2? R2 is actually simply R, which is unknown resistance over here. And this ratio is equal to say R3 by R4. R3 is actually 100 minus L1 into RCM. Okay, RCM here divided by R4 is your S. Okay, I'll just clean this side and then I'll write properly. I have understood which one is what. If I just simplify this thing, say RCM, okay, I'll just write again. L1 into RCM divided by R we have got, this is unknown resistance, unknown, which we have to calculate, and this is 100 minus L1, this is into RCM divided by S. This is the standard resistance which I can vary to get the null condition in the meter bridge. So this RCM can be yeah, we can remove that. So I have to find out R unknown. So from this you can write that this will be L1 divided by 100 minus L1 into S. Okay, so this ratio you can find out from the null condition of the galvanometer, and where the jockey is actually connected, that is AD, so that will give you the length of the wire L1, and this is 100 minus L1. So you know this ratio, and you have so in this case actually this is standard resistance S. It is written as standard resistance. It is actually a fixed resistance. Okay, here there is no change for this resistance. Once you connect, it will be fixed all the way. Where we are changing the resistance here, we are actually changing the resistance over here. Okay, see, just by varying the length of the wire, there we will be changing the resistance in the circuit and then finding out the null condition. So this is how you can find out unknown resistance in the laboratory using meter bridge, which based on or like working principle of this meter bridge is based on Houston bridge, balanced condition of the Houston bridge. Okay, I hope you people have understood this much. So now I have got another 20 minutes because I have started around at 6:10. So I'll try to tell you about the potentiometer quickly. So here also look, we will be using the Kirchhoff's KVL, okay, Kirchhoff's law, KVL. So what is the potentiometer? Actually, potentiometer is a versatile instrument. So as I told you that it can be used to find out. Suppose you have two cells, okay, two different cells. So suppose this has EMF U1 and it has EMF E2. Okay, internal resistance R1, internal resistance R2. So see, if I know the parameters for this cell 1, then I can, if this is unknown cell, I can find out what is the EMF and internal resistance, etc. Okay, I can find out that. Obviously, if I need to find out the internal resistance, I need to know the EMF first, EMF of the cell, unknown cell first, we have to find out. So there are two applications for this potentiometer. Before I go to the application part, let me tell you the construction of this potentiometer. So in this case also we will be using a long wire. We will be using a very long wire, very long wire. Okay, so I am actually discussing very basic things like Houston bridge, meter bridge, etc. But there may be many questions in questions, various type of questions asked in the exam. So those things we will be discussing in some other classes, or maybe I'll write the questions and upload in the WhatsApp group. You may find out the answer for that, or if you can't, you can ask me there also. I can answer. Okay, in fact, I'll give many questions on this crystal bridge, meter bridge, and potentiometer, and their application part is very important. Okay, both for your laboratory and for your theoretical exam also. For both, you need this not like sound knowledge of this. Okay, in fact, in the meter bridge there will be only numerical applications, but in case of potentiometer, they will ask you to derive actually. They will ask you to derive sometime. Okay, they will ask you to derive how to find out the EMF of an unknown uh, cell, and sometimes they will ask you to find out the internal resistance of any cell given. So this is a circuit. You can see circuit diagram of the typical potentiometer. So in the potentiometer also, see there will be a long wire, a very long wire. It is actually maybe much more than 1 meter. Okay, much more than 1 meter. Length of the wire can be much longer than 1 meter. But in this case, the whole wire is not connected in the circuit. How it is connected, like they see they have just cut the wire, so cut the wire in equal parts, maybe many parts. Okay, like that they will cut the wire of certain length, suppose L. Okay, everywhere they will cut like that in same length. The long wire has been cut many pieces of same length, suppose, and what they will do, all the cut pieces of the wire, they will keep parallel. They will keep like this with the equal distance, suppose, like this. And see, the ends will be connected with a metal strip, thick metal strip, like this. Okay, they will keep a metal strip to make the circuit connected. Okay, connected the wire. Okay, with thick metal strip like this, they will connect all the wires each other in the circuit. So now this is actually in series. Look, this is not a parallel circuit or something. This is series. So if you go up to here, maybe if this is L, this is L2L, and this much is maybe L by 4. So you get 2L plus L by 4. Okay, this much length is connected to the circuit. If your jockey is here, okay, if your jockey is here, okay, all right. So this is how the wire is cut into several number of pieces, and then they will be connected. uh, First they will keep parallel to each other, and then connect with thick metal strip. Okay, after connecting them, what they have done, so they have kept a rheostat, they have a battery. Okay, they have a battery, they have a rheostat, they have a switch. Okay, one end of the wire is connected uh, to the key, and that key is connected to the rheostat, and through rheostat it is connected to negative terminal of the battery, and another end of the wire is connected to the positive terminal of the battery. This is the battery. And look, if I want to calculate, and I have a two-way key. This is actually two-way key, two-way key or switch, two-way switch or key. See, I have two-way key means here. I am just zooming it up and showing. So suppose this is, see, so sorry. Suppose there is a circuit through this and another circuit through this. Okay, so this is a complete circuit, suppose, and this is also there is a complete circuit like that. Okay, so if this and this is connected maybe like this. Okay, this can be connected like this with this wire. This is 3, this is 1 and 2. So it can be connected to 1. That time this circuit will be, so this is circuit, suppose this circuit 1, this circuit 1 will be connected, and when this 3 is connected to 2, then your circuit 2 will be connected. Okay, this is 2, circuit 2, this one. So like that you can see in this, 2 OA key has an important role. in this experiment. Look, I'll just go quickly because we are running out of time. Okay, so you look here, this three, like third terminal of the switch is connected to a galvanometer, and galvanometer is connected to jockey. Same principle. I'll look the null condition. Null condition. In this case also, we look the null condition. Okay, null condition means what? There is no current through the galvanometer, no deflection condition for the galvanometer. So what I do? Suppose I have to calculate, I have to find out what is the EMF of the cell 2. Okay, I have to find out. See, this wire is uniform. Okay, the wire here we have used is uniform, and suppose the potential drop per unit length is this. Okay, potential drop per unit length is 5. Okay, if this is the total length of the wire, this is the potential drop per unit length. Okay, for the wire. That means if you know the length where the null condition is achieved, then you multiply the length of the wire, you get the potential drop across that. Understood? Okay. Or EMF you can find out. Okay, you can just multiply with 5 to get. So you multiply with 5, so you will get the EMF of the pattern. Okay. So from here also you can find out EMF means voltage. Again, voltage drop. If you okay, so there are two things, EMF and voltage drop. We have, I think we have already discussed, if you have the cell electrodes, suppose two electrodes are there, and if so this is positive, this is negative electrode. Okay, now if there is an external resistance connected and current is flowing through that potential across this terminal will be V. Okay, which can be written as I into R. And if there is no current to that, okay, then the potential across this P and E will be E. This is called EMF of the battery. Okay, and this is called terminal potential of the across the cathode and anode. Okay, across the two terminal, and they have a relationship. Okay, they have a relationship like this. V is actually this minus I into R. This R actually is the internal resistance for a cell, because when current I is passing through the external circuit, suppose this is capital R, in the electrolyte also the same current is flowing in the opposite direction. Okay, same current is flowing, and in the electrolyte, suppose there is some resistance, so there will be a drop in that. So this is the total EMF of the battery when there is no current through the external circuit, but when there is a current in the external circuit, the EMF of the battery will be this. Okay, this, so that will be equal to the terminal potential. Okay, when there is a current going through the circuit. So we know these things, so which will be applying over here. So look here, what we'll do, we'll just take a loop over here. See, first we'll see, we have a standard cell. Suppose E1 is the standard cell. I'll just see the null condition for that. So I'll connect this 1 and 3. 1 and 3 will be connected now in the 2A key, so that I get the circuit. See, I can get A to 3, 3 to G, G to N1. So at this condition, we have got the null condition. Okay, or in other way, I can add A, N1, G, 3, then A. So this is suppose loop 1. So A to N1, okay, and go G to 3, and then cell U1, and then A. This is the loop. Suppose first case when I get the null condition for. Okay, so with the cell 1, I am getting the null condition. Okay, I can write down my KVL over here. So KVL means, see, suppose this A1 length, AN1, this is the length is connected. See, I am going through this with the jockey to find out the null condition, and at this length I have got the null condition. If I say this is L1, this is L1. Okay, if I say this is L1, so L1 into 5 will be the EMF. Okay, okay, or the voltage drop across this potential drop across this, which will be equal to the battery EMF. Okay, and see there will be no drop, potential drop across this galvanometer. So I can directly write this is, see, it is going. So this cell, we have learned that if I go in this way, that means current is going out from the positive electrode. Okay, then the EMF has to be taken as positive. So I have got this. This is E1. Suppose I just connect my 2 and 3, this one. If I connect like this, now see the cell 2 is connected to the circuit. Now I'll see for the loop 2, that means your AN2, see now your null condition is AN2, loop AN2, N2, then go to G, then go to your 3 to 2, then your cell E2, then A. This is the path of the loop. Now see, I can write, if this length is AN2 is L2, so AN2, suppose the length is L2. Okay, so L2 into phi. So L2 into phi is the potential drop, which is equal to the EMF of the battery, that is E2. Okay, I hope you people are understanding. If you now read the book, you will be understanding again properly. So because there is a shortage of time, I'm just going a little faster maybe. So I can take the ratio from here, see E1 by E2 from these two equations, 1 and 2. So if I take the ratio of this, look what I'll get. L1 by L2. I'll get like this, because the EMF is directly proportional to the length in this case. Now look, if I know this, if this is a standard cell and this is unknown EMF of the battery, so look here how I can find out. L2 by L1, I have to take the ratio, and with that multiply this E1, that is the EMF of the standard uh, battery, which I actually should know. So if you are given a standard cell having EMF U1, and you have to find out the EMF of the other cell having EMF E2, using this formula, practically if you find out the null condition, okay, that means you will get the length of the wire for two null conditions and take the ratio of those two and find out, okay, find out the unknown EMF of the battery. So by doing that, okay, in fact by comparing the null condition of the two cells, I can find out the EMF of unknown cell. If my E2 is unknown cell, so from here, from this ratio, I'll get this is L2 by L1, okay, L2 by L1 into E1. This is standard cell, I know this, and this L2 and L1 I will be able to get from the null conditions of the uh, null conditions from the experiment. Okay, I'll just go another 5 minutes to finish this chapter. I don't want to again hang on this chapter. Okay, so hope you have understood this. If not, you just can ask me later, but you should read it. uh, I hope you will be able to understand once you read now. So now look, as I said, there is another application of this potentiometer, so that I'll not write from here, I'll just show from your book itself. Let us, so if I write, it will be actually I'll be taking a little extra time maybe, so I'll not write here. I'll just directly show from your book and then tell you the situation. So in this case also same thing, but a little difference. There is a little difference in the circuit. You look here, so little difference. Suppose I have been given a cell for which I know the EMF. I know the EMF, but I have to find out the internal resistance for that. So the circuit diagram, look here. Here also, see here, the same thing actually. So this is the same potentiometer here. This is the potentiometer. Now what you have to do? you have to connect the cell across the cell. You have to connect a standard resistance box through a key K2. Okay, so they have to be in parallel. Okay, cell and this standard resistance has to be in parallel. Now look, once you keep this K2 switch open, then in the circuit your only cell is connected. Okay, so in the beginning what we'll do, in the past what we have to do, since we know the EMF of the battery, we'll be again applying the KVL over here. So see, we have to find out the null condition. When my K2 is open, that means your resistance box is not connected in the circuit now, not connected to the circuit now. Now see, your only cell is connected and this length is there, length of the wire is there. So what you can do, you can find out just by sliding your jockey and tapping everywhere and see the null condition. That means there will be no deflection. No deflection condition, you have to find out at which length of the wire you are getting the null deflection or zero deflection. So I just go from, I start from A and slide over the wire, and maybe we get null deflection when only the cell is connected, that is here at AN1. Okay, where I can take the length of this length, maybe L1. Okay, maybe L1. See here it is written. Similar thing, what I'll do now, I'll just close the switch here K2. Okay, K2. Okay, now I have not told you the use of this rheostat. Rheostat you can use to rheostat means variable resistance. See, this is a battery and rheostat is connected. That means if you change the resistance, the current what you flow in the potentiometer circuit will be controlled by this rheostat. Okay, so that part is there. You just read this book. Okay, you will understand. Now, after closing the switch K2, the same thing I am doing. What I am doing, I'm just finding out the null condition for the potentiometer bridge. Okay, so suppose so how do I get the null condition? See, null condition immediately you will not get. What you have to do is, see, this is standard resistance box. What is standard resistance box? There will be many resistance keys. Key will be there. Once you just open a key, that resistance will be connected to the circuit. Suppose you just keep on choosing various combinations of the keys in the resistance box, where you can find we know the resistance there. Okay, so you just find out a proper combination of the resistance keys in the standard resistance box such that you get a null condition. And suppose the null condition is at AN2. If this is the length L2, then I can write the KVL for this circuit. Okay, KVL for this circuit. Look how we can write. I have defined. Okay, so now see, in the first case I have got phi into L1. In the second case, I get what I get actually in the second case. See, as I told that when there is a resistance connected across the battery, that is external resistance here, the standard resistance box. So this EMF, actually we should not write E. Now you have to write the terminal potential. That's why I have written over here. Instead of writing E here, I have written phi into L2, that is equal to the terminal potential between this cell, across this cell. Okay, terminal potential of the cell. So that's why I have written V over here. You should not be confused with E and V. So in the beginning, in the first case, I have only the cell. There is no resistance connected from the externally to flow the current from the cell. Okay, but in this case, when you connect the battery across this standard resistance box, across this battery, then the drop across the resistance will be equal to the terminal potential of the cell. So that's why it is written here V. Now if you take the ratio of V and this, see, you'll get a value. See, E by V, or E by V will be L1 by L2. All right. Now I know the relation between terminal potential and this. See, this is the relation between the terminal potential and, see, as I said, maybe this question I'll tell you what. I'll write it here. Okay, here. So I have, sorry. So I have got E is equal to phi into L1 and V is equal to phi into L2. Okay, so E by V is equal to L1 by L2. This I have got already. Now see, I know the relation between this. See, as I told, this is this is internal resistance. This will be equal to terminal potential, which I can write as I into R. The resistance I have connected here to get the null condition at N2 is suppose R, and maybe the current flowing through the circuit is I. So this is why I can write like this. Okay, now look what I can write. So I can write this as uh, E is equal to this. I can write. Now see, I know this is IR, V is equal to IR. So if I get the ratio E by V, what I'll get is uh, R plus R divided by capital R. So I get cancelled. So I'll get 1 plus R by, sorry, small r by R. Okay, small r by capital R. Okay, this I have got already. All right, so I have to find out. So E by V, again this I have got. So I can just equate these two, because I know nothing other than, see, in the practical or laboratory exam, I know nothing other than this length and capital resistance R, capital R. I know only that. So I have got this is equal to L1 by L2. Okay, so from here you can find out this is L1 by L2 minus 1. Okay, and so if I simplify a little bit, simplify means just I have to find out this is internal resistance small r. I have to find out, multiply capital R, which I know already from the resistance box. This is L2, and this is the L1 and L2 are the length of the wire where we have got the null condition. Okay, or no deflection condition. Okay, so using this formula, you can easily find out the internal resistance of the given cell. Okay, so these were two applications for this potentiometer. I hope you people have understood this. We'll be doing many numerical example as well as many other applications depending on this. So thank you all of you for your patience. I think many new faces are also there. I hope they will give their feedback to Guna madam or someone. Okay, so I'll stop it here. I have taken some 8 minutes extra, but yeah, I had to finish this chapter. Okay, all right. So I think we'll meet again on Wednesday. Okay, guys, bye. I'll be speaking through WhatsApp, like giving some tasks to you people depending on this potentiometer base, Wisdom base, and etc. So try to solve those problems, and we'll just take some some repetitive problem to discuss in the class. Okay, all right.